Okay, in this video we are looking at gas laws practice number 1, starting with number 7, which is the gay-lussac law problem. It says the pressure in a car tire is 1.88 atms at 25 degrees Celsius. So here's a pressure, P1, and a temperature, T1. What will be the new pressure? So we're looking for P2. If the temperature warms up to 37 degrees Celsius, so that is our T2 value. So, we are using gay-lussac law, but if you weren't sure of that, then write out your gas law, PV over NT. And then we need a gas law with pressure and temperature. So we want P over T equals P over T. P1 over T1 equals P2 over T2. So there's our gas law that we need right there. Okay, so before we substitute in our values, we know that we need our temperature for any gas law to be in Kelvin. So our T1 value is 25 plus 273 gives us 298 Kelvin. And then our T2 value is 37, so 37 plus 273 gives us 310 Kelvin. And now that we have our temperatures in Kelvin, we can substitute into gay-lussac law. So, P1, so 1.88 atm over T1, which is 298 Kelvin, equals P2, which we don't know P2, so we're going to substitute in X, over T2, which is 310 Kelvin. So of course we're going to need to cross multiply. So 1.88 times 310. 1.88 times 310 equals 298 times X. And we are leaving off our units here. Our final answer, just to take a look at our units, Kelvin's going to cancel out. And our final answer, our P2 value, will come out in ATMs, so some number of ATMs. So to isolate X, we need to divide by 298. And we do this on both sides. So these 298s cancel, we're left with X on the right hand side equals 1.88 times 310 divided by 298. Let's put that in our calculator real quick. 1.88 times 310 equals 582.8 divided by 298 gives us 1.9557. And our units are, of course, in ATMs. So let's look at our answer choices and find the one that is the closest to 1.955. 1.96 ATMs is very, very close, so that is our correct answer there. Alright, our next problem is number 8. If a gas sample has a pressure of 30.7 kilopascals, so that's our initial pressure, at 0 degrees Celsius, so there's a temperature, our initial temperature, by how much does the temperature have to decrease to lower the pressure to 28.4 kilopascals? This is our P2. So the problem isn't actually asking us to find T2 directly. It's asking us to find T2 and then to find the change in temperature. By how much does the temperature have to decrease? So what is the difference, basically, between T1 and T2? What's the difference between these two values? That is what this problem is asking us to find. So we are going to have to start by solving for T2, but then our answer isn't going to be T2. That's not going to be an answer choice. The answer is actually going to be the difference between T1 and T2. So, to use gay-lussac law, P1 over T1 equals P2 over T2, we do need our temperature to be in Kelvin. Of course, we're looking for T2. That will come out in Kelvin once we convert our T1 to Kelvin. So, since our T1 is 0 degrees Celsius, our temperature in Kelvin is 0 plus 273, which will be 273 Kelvin. So that was nice and easy. Our pressure, our P1 is in kilopascals, and our P2 is also in kilopascals, so we can leave those units of pressure alone since they are consistent. All right, so P1, 30.7 kilopascals, over T1, which is 273 Kelvin, equals P2, 28.4 kilopascals, over T2, which we don't know, so we're going to substitute in X. Now we need to cross multiply 30.7 times X, and I'm going to leave off my units, equals 273 times 28.4. Now that we've done this, to isolate X, all that we need to do is divide by 30.7. And whatever we do on one side, we must do on our other side as well. So we're going to divide by 30.7 on both sides. The 30.7's cancel out, and now we have X equals 273 times 28.4 divided by 30.7. 273 times, move this over just a little bit, times 28.4, enter, divided by 30.7. And that gives us a final answer of 252.547. But of course this answer is in Kelvin, so we need to convert this back to Celsius. And to convert to Celsius, we do have to subtract 273. So 252.547 minus 273, that's going to give us a negative value. So it equals negative 20.45 degrees Celsius. So that's our value for T2. T2 equals negative 20.45. Now to find the difference between T1 and T2, T1 is at 0 degrees Celsius minus negative 20.45 degrees Celsius. So the difference, the delta T, is going to be equal to 20.45 degrees Celsius. And this does work out. We didn't really need to do the subtraction because we are starting off at 0 degrees Celsius. So the temperature change is 20.45 degrees Celsius, which is very close to 20.5, letter A. This last problem says helium gas in a 2-liter cylinder is under 1.12 atms of pressure. At 36.5 degrees Celsius, the same gas sample has a pressure of 2.56. What was the initial temperature of the gas in the cylinder? Okay, so we have a lot of pieces of information in this problem. Some of them matter and some of them don't really matter. So let's go through and list out everything we have. So helium gas in a 2-liter cylinder. So that's a volume, probably a V1 value. Initial volume is under 1.12 atms of pressure. So that is a pressure, a P1 value. V1 and P1. At 36.5 degrees Celsius, the same gas sample has a pressure of 2.56 atms. So this is a new pressure, a P2 value. And since the temperature is going along with this pressure, this must be a temperature, but it must be the second temperature. It must be a new temperature. So we don't know what the initial temperature was, but we know what the new temperature was. And it's the same gas sample, so it's still in the same cylinder, presumably. It has in the cylinder, the 2-liter cylinder with the same volume. So our volume must still be 2 liters. That must be our V2 value as well as our V1. And then the problem's asking, what was the initial temperature of the gas? So what is T1? Okay, so here we have some pressures. We have 2 pressures. We have one temperature, and we're asked to find another temperature. And then we have a volume listed, but the volume is staying the same. So we don't really care at all about the volume because it's holding constant. The only variables that we're interested in looking at are the ones that are changing. So now that we've read the problem carefully and we know that volume is staying at 2 liters, it's consistent, I'm just going to cross these bits of information out because it's kind of extraneous. We don't really need that piece of information to solve the problem. So the ones we're interested in are P1, T1, P2, and T2. So looking back at our gas law, PV over NT, we need a gas law that relates pressure and temperature only, while everything else is held constant. So I'm going to circle P and T. And so the gas law that we need is P1 over T1 equals P2 over T2. And that's good because this was supposed to be a gay-lussac law problem, and that's the gas law that it tells us we are supposed to use. So clearly we're doing something right so far. Alright, so we know to use a gas law we need our temperatures to both be in Kelvin. Or actually this time we only have one temperature, but we need our one that we have to be in Kelvin. So our T2 value, 36.5 plus 273, 36.5 plus 273 is going to give us 309.5 Kelvin. And then our T1 value is also going to come out in Kelvin. Alright, so now that we have our temperature in Kelvin, we can check our units of pressure. Our P1 is an ATM, our P2 is also an ATM, so we don't need to do anything to those values, so we can substitute into our equation. P1 over T1, or 1.12 ATM, over T1, which we don't know, so I'm going to substitute an X, equals P2, 2.56 ATM, over T2, which is 309.5 Kelvin. Now we need to cross multiply. 1.12 times 309.5. I'm going to leave off my units this time. Equals 2.56 times x. To get x by itself, we just need to divide by 2.56, and we need to do that on both sides. And so we're left with x equals 1.12 times 309.5 divided by 2.56. And that gives me 135.406. And of course my answer for T1 came out in Kelvin, so I'm going to put Kelvin next to it. Now, my answer choices are not given in Kelvin, they're given in degrees Celsius. So to get Kelvin into degrees Celsius, I need to subtract 273. 135.4 I'm going to round because my answer choices are only rounded to whole numbers or one decimal point, minus 273. And so this is going to give me a very negative value. It's going to give me negative 137.59, which I'm going to round to 0.6 degrees Celsius. So I'm looking for an answer choice that's very close to this value, negative 137.6. Theirs is rounded incorrectly, but it's very close to answer choice B, which is the correct answer there. But we had to convert back to Celsius to get the correct answer choice.